Dear colleagues, hello. Let us begin our seminar. Our today's talk is Vassily Manturov, and he will tell us what will he tell us about.
Well, I'm planning to talk about GNK, the groups GNK, and an approach towards invariants of links. Okay. And now it's turning 10 years since the groups GNK were discovered. And those families of those two parametric families of groups were devoted to constructing invariants of configuration spaces. Namely, we were looking at configuration spaces of some particles in a certain space, and the first key example we handled at that time was the usual braid group. So in general, 10 years ago, I formulated the following principle. If dynamical systems describing a motion of n particles have a nice codimension 1 property, which depends exactly on k particles, not more, not less, then these dynamical systems have a topological invariant valued in GNK. Well, today, I will decipher it during the talk. I will tell what happens with braids, and actually, the first key example we have is related to maps from the braid group, or maybe pure braid group, to the groups GN3 and GN4, with the property being 3 points are collinear or 4 points belong to the same circle or line. Well, now I'm planning to define the groups GN3 and GNK, and actually the group GNK has generators, has choose NK generators. So in Russian and French notation, we usually write C and K for choose NK. So that's where my notation for the group with as many generators, with that many generators comes from. And the generators correspond to k element subsets of the set from 1 to n. So these are generators, and relations in that group are divided into 3 parts. The first family of relations says that all generators are involutions. This makes GNK very much related to braid groups, and very much related to Coxeter groups, excuse me. We can get rid of it, but I don't want. And the second relation means far commutativity, which says that if we have 2 sets of indices, k element subsets, which have intersection, not maximal intersection, their intersection has cardinality less than k minus 1, then they have to commute. For example, in GN2, they commute if we have if they do not have any common indices. In GN3, they may have one common indices or nothing. And the most important relation is as follows. So if we have a k plus 1 indices, then we can choose any k of them, and there will be k plus 1 subsets. I call them M1, M2, and Mk plus 1. Then such a product is equal to itself in the opposite direction, or we can write this product squared equals 1. So these are groups I'm working with, and though these groups work very effectively when we deal with configuration spaces of points, or maybe lines, or maybe some other objects in some spaces. But actually, they work for braid-like objects. When we have a dynamical system with a fixed number of generators, like endpoints move on the plane, or some lines move somewhere. But it doesn't work nicely from the very beginning. It doesn't work nicely for knot-like objects. So, for example, if we have a knot, we can certainly scan it from the top to the bottom, but the number of points can change. It can change by 2 when we go through a maximum. And of course, if we have a knot, we can split it into braids, as people usually do in the Kontsevich integral. And then we may try to get some invariants of braids in those segments when we have maxima and minima. And today I will try to construct invariants of links. Not yet knots, but links. Okay, so for k equals 3, the main relation looks as follows. So we have 4 indices, ijkl. Well, excuse me for using k as a number and an index. And then the relation looks as follows. So we take ijk, ijl, ikl, jkl, which equals a jkl, ikl, ijl, ijk. So this is the main relation in GN3. And similarly, you can have relations in GN4, which will have length 5. Then we can do the following. If we have a braid, we can represent it as moving points on the plane. So we may have some moving points and take some horizontal plane. And as points move, we draw how they move and get n strands, n non-intersecting curves. And for each level, we have some points on the plane. So now we are interested in the following property. 3 points on a plane are collinear. And now the way of constructing an invariant of braids valued in GN3 is very easy. So we take a generic braid. I will say what a generic means in a while. We take a generic braid, and when 3 points appear to be collinear, I write the corresponding generator. So if those points are I, j, and k, I just write a, I, j, k. And here, genericity means that those triples of points behave nicely, meaning that there are only discretely many of them. They're all transversal, and there are no quadruples of points at one moment. And if we have one triple of points, then no other triple is collinear at that moment. Okay, so we have some codimension 1 event, and actually the main theorem for G and K is proved, and the main principle corresponds to a very simple fact. So if we have some configuration space, like the space of points, of collections of points, or maybe collections of lines, or maybe this space can be infinite dimensional, then we may have some way of splitting this space into chambers. So we have some codimension 1 walls, and those codimension 1 walls meet at codimension 2 crossings. And if we want to consider a homotopy class of a path here from one point to another, then generically it passes through walls, but doesn't pass through crossings. So if we have such a generic path, then if we are able to put some labels on walls, then for such a path, we write down the product of corresponding labels, right? And so what happens if our path is not generic? Well, there can be some tangency, and if we have some tangency, then two intersections occur when we get a little bit here. And there will be some relation saying, for example, that this generator squared equals 1 if we do not pay attention to the orientation. And if we do pay attention, well, it may mean nothing, but in our case of G and K, I just do not pay attention to the orientation. So that's why yeah. And one more thing is as follows. So we can go around the corner, and then we should write down all generators, all walls which appear around this corner. So these are typical relations, and well, there can be configuration, there can be paths from one fixed point to another, and we can consider homotopy classes, or there can be loops from a point to itself. Well, so this is the general setting, and now the codimension 1 property. 3 points are collinear. What about codimension 2 properties corresponding to that one? So first, there will be relations something squared equals 1. So this means that if we have 2 points on a line and say some third point goes this way and touches itself, so we may assume that there are braids and there is a generic isotopy between those braids. And before the isotopy, there is no intersection. After the isotopy, there are 2 intersections, okay? So we have this. And so this means that any generator squared equals 1. And also, what about codimension 2 relations? Well, it may happen that we have some 3 points on a line, 1, 2, 3, for example. And for example, it may happen that 1, 4, and 5 are on another line. And what happens in codimension 2? Well, we can have this corner. And if we consider a generic path, we can go around this corner. And this means that our point 1 can go to 1, 4, 5, and 1, 2, 3, and 1, 4, 5, and 1, 2, 3 again. So this is exactly this relation. Of course, it may happen also that 2 different lines contain 2 well, indices. There are no common indices at all. So this is the relation here. But the most interesting relation comes from the codimension 2 event when when some 4 points are collinear. So this is a relation of codimension 2, and 4 points which are collinear. This situation is unstable. So if we have a generic braid, it never happens. But if we have a braid which is not generic, it may happen. And if we perturb it a little, this quadruple point disappears, but 2 triple points do appear, 4 triple points, 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4, and they will appear in some order if we perturb in one direction, and they will appear in the opposite order when we perturb in the other direction. And that's what these relations come from. Okay, and also in quite a similar way, we can do a map from the pure braid group to GN5. GN4, excuse me, with the main property being 4 points belong to the same circle or line. So this is another property, and again, we will have just a similar thing. Well, you may ask whether this map from braids to GN3 or GN4 is a homomorphism. Well, not quite. It will be a homomorphism for pure braids, and for non-pure braids which are not pure, we can just permute indices when we map one braid to GN3, so the product will not become very nice, but there will be something like a semi-direct product, and it's quite easy. Okay, and now I'm going to tackle the question about, well, by the way, the text you see here is our book, Invariants and Pictures. So it is published in World Scientific in the year 2020. And the authors are myself together with Denis Fedoseev and Sonjong Kim, and also Igor Nikonov. So this is a book, and actually GNK have a long story from 2015. And in this book, you can consider a long theory of GNK, but everywhere we study some configuration spaces of some points or lines or something else when the number of objects, the number of particles does not change as time goes. Now let's pass to the main question. And the main question will be what to do with links. Well, of course, it's well known that knots and links are equivalence classes of braids modulo Markov moves. I just recall that Markov moves are of 2 types. One type is just conjugation. So if we have an n-strand braid, then we conjugate it and get to that, to a braid like here alpha and here alpha to the -1. And the other relation is the other equivalence is given by a so-called stabilization. So if we have a braid beta on n strands, then we can add another strand and intersect it with the last strand of beta. Well, never mind with crossing drawn like here or the opposite crossing, and these are positive and negative stabilization respectively. And the question is how to extend this GNK map to the Markov moves. Well, those who have never heard of GNK may ask the following questions. First of all, how effective these groups are. And well, of course, if we have a mapping from one group to another, people may ask, well, these groups are, the target group is complicated. How do we know what happens with this group? But actually from G and K, there are lots of homomorphisms to free products of Z2s. And you know, if we have at least 3 Z2 factors, then this group is already very interested and easy to work with. I mean, this group has exponential growth, so it's big enough. And also, the word problem in this group is trivial. So this means that we can get invariants of braids very quickly, and they are powerful enough. Well, some more questions that people who are not aware of G and K may ask is whether this map G and K, the pure braid group to G and K, GN3, is injective or surjective. By no means it is surjective. GN3 is much richer than braids. Is it injective? Not quite, because if we have endpoints on the plane, with not all of them being not 3 being collinear, then we can rotate it as a whole, make a whole revolution. And this, of course, there will be no collinear triples at all. And this is the braid. This is the braid which generates the center of the pure braid group. And up to that center, it is almost proved that there is no other kernel. But so far, the proof is not finished. So it is almost injective. And also you can ask me whether the word problem in GNK is solved. Unfortunately, it's solved only in partial cases like GN2 for any n and GK plus 1K and G53, I think. Otherwise, it's an open problem, okay? Now I want to tackle knots and links. So I assume I have a knot, which is given as a closure of something. Of course, if I look at braids and want to deal with conjugacy classes of braids like this, then of course, if I have a map which is homomorphism, everything gets conjugated. But here you see there is a subtlety. The subtlety is that my indices on the top are not quite the same as on the bottom. Well, if we have a word in, say, free group or free product of Z2s, it's not a great deal because, for example, if we know the permutation, we know that we cannot quite conjugate, but make a skew conjugation like this. We put some A. So if we have some word W, we put some A here, and not quite A, but phi of A to the minus 1. So such a problem for free groups can also be tackled. So if we deal just with the first Markov move, it's easy to get lots of invariants out of it, out of GN3, and similarly out of GN4. But if I want to deal with the second Markov move, I get in trouble. Why? Well, because the number of strands is not fixed. Assume I have a knot. Assume I have a one component knot, which is encoded by a closure of a 4-strand braid. How many indices should I have here? Well, people may ask 4. But when I add another strand, what should I do with that? So if I perform the Markov move here, should I have 4 indices or 5 or maybe something else? How many? That's a problem. So we should not look at braids. We should not look at groups, excuse me, because knots are do not form a group, unlike braids. Well, then we can ask, okay, maybe not a knot, but a link. For example, if I have a 2-component link, or maybe 3-component is better to deal with GN3. So, for example, I can get a 3-component link like this. And so I use 3 different colors, like here, here, and there. So here I have a 3-strand braid whose closure is a 3-component link. But now I can perform the Markov move. In this situation, at least I see clearly which strands I have. And I may try for an n-component link to use n indices, so 3 indices here. Well, 3 is not good for GN3, but maybe we can say, okay, let us have yet another strand like here, an orange strand. Okay, we move on the plane and we try to draw generators. Generators correspond to colors, but oops, here, red points. There is not one red, so the number of red points is 2. And what does it mean? It means that if I have, for example, something like blue-red line, there will be 2 such lines passing through this blue point. And it may happen that on one blue point, on one line, I have a green generator, and on the other line, I will have an orange generator. So these are 2 different lines. But how is it expressed in the language of braids? Well, in the language of braids, it is expressed as follows. So if this is 1, 2, 2, and 3, and this is 2 and 4, then I have to write that 1 to 3 commutes with 1 to 4. And these are very bad news because then everything will have to commute. And the group will lose everything. So good news about GNK is that they are very far from being commutative. So how to handle this situation? Actually, one can do many things for knots and for braids. For example, one can try to get a chord diagram. Maybe those of you who are familiar with the Kontsevich integral may remember that first, the Kontsevich integral can be easily defined for braids by putting some chord diagrams and integrating something. And after that, we close such picture to get a chord diagram on a circle if we have a knot, or on several circles if we have a link. So we get a chord diagram. Is it possible to do the same for GN3? So somehow, morally, the usual arting presentation of the braid group is an upgraded version of GN2. Because if we put a usual crossing for between 2 strands, this means that 2 points have the same x coordinate on the plane, OXY. So it depends on 2 coordinates, but it contains some more information than just GN2. Okay, so we can close up our arc diagram on several strands to get a chord diagram on a circle. Can we do the same for GN3? Of course we can, but there will be the following trouble. You see, if I have, for example, 5 strands, 1, 2, 3, 4, 5, and I consider chords 1, 2, 3, and 1, 4, 5, they have to commute. But if we try to draw it on a circle, then these triple chords will have just one adjacent end, right? And those ends, we can permute those ends. So combinatorially, if we allow to permute two ends on a diagram, everything will be lost. And I have to, then I will have to describe somehow that there is some height issue that we can permute two triple chords only in the case when they have the same height, but it's hard to draw height here. We want everything to stay combinatorial. One way to overcome it can be as follows. Instead of n points on the plane, we can consider yet another configuration space where a point in the new configuration space corresponds to 2 points. So, for example, those 2 points will correspond to the index 1, 3. And those 2 points will correspond to the index 2, 4. Of course, there will be choose and to generators. We can draw them as choose and to vertical lines. And then if we draw chords, well, you see, instead of 1, 2, 3 chord, there will be a chord between 1, 2, 1, 3, and 2, 3. And the good news is that if I have, for example, 1, 4, 5, then these chords will be 1, 4, 1, 5, and 2, 5, having no indices in common. And this is really good news because combinatorially there is no problem to move these chords. But there is another problem here, meaning that I don't know how to close it up. So there is some randomness in closing. So, for example, if I have 1, 2 here, and how to connect it to 1, 3, or maybe to something else, I don't know. Well, there is yet another way of trying to handle the situation for knots. And this way is as follows. So we can consider a Morse embedding of a knot, as in the Kontsevich integral case. And in the Morse, for the Morse embedding, I can have those horizontal strips, and inside any strip I can get braids. But you see, in this situation, again, I don't know which indices to take. So, for example, I have, so here I can have 2 strands, and there I can have 4 strands, and so on. So maybe I realized, maybe I told you about several ways of tackling and why they do not work. But now a very easy construction came to our mind, and this easy construction uses it's a research in progress with Igor Nikonov. And well, there are no pictures here, but the idea is as follows: we take a map from we represent a knot, a link, excuse me, by a closure of a braid. And if we want to have such a link, we can do the following. My link can be an n component link, and it can be represented by n capital component braid. So n capital can be strictly stronger than n small, and we have something like that. Something is colored, some strands are colored, and for example, those guys are colored black, and those guys are colored red, and those guys are colored green. Okay, and this is a colored braid, pure braid, excuse me, and I can close it. How do I close it? Well, I can assume that we have n capital strands going as they go in the braid, and also I have almost vertical strands which go a little bit behind. So, for example, this green end is connected to that green end by something behind our braid. Okay, now what to do? What to do with our moving points? Well, initially there were three components of our link, but the number of points here will be 12. What can we do? We can choose any three of them. But actually, if we have, for example, more than three, so how can we get rid of that ambiguity? So you remember the ambiguity was as follows. So I had points on the plane, and some of them were colored, say, black or green or red. So maybe 1, 2, and 3. And the problem was that I can have a straight line 1, 2 here, and a straight line 1, 2 here, 1, 2 there. And then this 1, 2, well, maybe I can add some fourth color. Maybe this 1, 2 contains 4, and that 1, 2 contains 3. And this will be the problem. What can I do to fix it? I can just fix some 3 indices, 1 and 2 and 3. So this means that I choose 3 points, 3 colors among those 12 ones. Okay, and if I choose those points here, I can look at the following. I can look at points moving at 3 points moving here as 1, 2, 3, and I can look at colors at points of all other points, for example. And I'm interested in those situations when 1, 2, 3 are collinear. Exactly those 1 and 2 and 3. I don't pay attention to other 1, 2, and 3. And I may be interested in the situation when 1, 2, and something is collinear, or 2, 3, and something are collinear, or 1, 3, and something are collinear. And I can write down similar generators. Okay? So this means that I very much reduce myself, but when I reduce myself, I want to I will get rid of the problem that one line passing through 1, 2 of problem of 2 different lines passing through 1, 2, because there is exactly one chosen point colored 1 and exactly one point colored 2. And these are good news. And then I will be interested only in generators 1, 2, 3, and also 1, 2 something, and also 1, 3 something, and also 2, 3 something. And then I just do, and then what I do is I write down this word, maybe only in 4 generators, for each strand, for each choice, and then just take a sum of those choices. What do I mean by a sum? I have group elements. And if I have group elements, I can do the following. I can just take the formal group ring with, for example, z coefficients of, or if I'm lazy, I can take z2 coefficients. And also, I will consider elements up to conjugation. Well, so here I have the following. So here is the formal definition. So let beta be a braid on n strands. We realize it geometrically as I drew by 2n strands. And the points here should lie on the circle. Well, usually there is a standard way of representing braids when points on the top are connected to points on the bottom, and those points as a fixed point in the configuration space lie on the line. But this is not very good for us because we don't want to have triple points on many points on the line. So we prefer to put them on a circle. This is just a choice of the initial point in the configuration space. Then we add yet another strands here. Again on the unit circle, and we have such a cyclic ordering. So we assume that they are ordered cyclically, 1, 2, and so on. And there is a line which separates points from the first n indices and other n indices. And so then we have those guys where the braid is interesting, and those guys where the braid is trivial, which corresponds to the closure. And then we may assume that, somewhere on the top they are connected. And then we take the following. We take this closure and choose this. So here, maybe you don't understand something in this notation, but actually from the GNK group, GN3 group, I extracted something by using MN indices, and now I will tell you what I mean. Well, in fact, I take the group ring not quite of the group GN3, and better to say that this will not be a group ring, but this will be a Z module or Z2 module of some sets. So I consider some equivalence classes of some group elements modulo some equivalence. So there will be a certain set. And the group will not be GN3 itself. It will be an easier object. And then I will consider some moduli space of linear combinations of some objects. I will tell you what they are in a minute. Modula some automorphisms, conjugacy classes, conjugacy, and index permutation. So simply it will look as follows. Simply it will look as we take some group Z2, 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 and so on, some free product of those groups. How many of those groups I will have, I will tell in a minute. And if I have such groups, I consider the conjugacy classes. Well, conjugacy classes are encoded just by cyclic words. And they're also, well, the conjugacy problem in that group is also easy. And also I use an equivalence by permutation of indices. So for example, if I have a word in indices A, B, C, and D, like this, and I can permute indices, then from here, I definitely can get to something like, B, A, C, C, B, A, B, C, B, D. But I can never get to some word with, say, C cubed with 3 generators in a row. Okay, so the objects which generate my Z or Z2 module will be very easy to recognize. So they will be made out of equivalence classes in a group, and the group will be very easy. And what are those easy groups? I already mentioned that there are lots of homomorphisms from the group GN3 to many free products of Z2. What are those homomorphisms? And those homomorphisms are very easy. Well, assume I have a word in GN3. Then I can have a generator 1 to 3, for example. And well, I can look at all occurrences of 1 to 3 in my word. There are many generators 1 to 3. Is it possible for those generators 1 to 3 to get close to each other and then to cancel by the relations 1 to 3 squared equals 1? Well, to that end, we can count the number of generators 1 to 4 and the number of generators 1, 3, 4 and the number of generators 1, 2, 3, 4 and count only those mod 2. So I will get 3 numbers mod 2. And if I perform my relation in GN3, then those 3 indices, those 3 parities will either stay the same or all switch. So this means that I look at those 3 indices, they form a discrete binary cube like this. And in this binary cube, I have opposite vertices. So, and if 3 indices correspond to some vertex, they can jump to the opposite vertex. And this means actually that any generator of the type here of 1 to 3, any generator can get an additional index. So for example, here I just write down 0, 0, 0, which is the same as 1, 1, 1. And then between these 2 generators, I can count the number of 1 to 4, 1 to 3, 1, 2, 4, 3, 4, and I can count them mod 2. And if those three numbers are 0, 0, 0, or those three numbers are 1, 1, 1, then those guys have a chance to get canceled. Otherwise, they are not. So actually, from here, we see that 1, 2, 3 can get additional indices, and I will get at least Z2 to the 4. But also between two adjacent 1 to 3, there will be indices coming from 5. If I have 5 strands, I mean, I count 1 to 5, 1, 3, 5, and 2, 3, 5. Any questions?
Excuse me.
Yes.
Sorry, here in the section 3, on the first line, xi
Yes.
goes to R3.
Oh, yes, sure. Yes, sure. Yeah. It's a typo. Yeah, sure.
Then the next R2 is also R3.
Okay.
Oh,
Thank you very much. Well, this is just a sketch where it's a work in progress.
Sure.
Yeah. Okay. Now, we have lots of indices, and any horizontal trisecant, which is 1 to 3, well, there are different types of trisecants. To have some feeling of those different types, we can consider trisecants from the following point of view. We may have a trisecant where 2 is in the middle, or we can have a trisecant where 1 is in the middle, or I can have a trisecant where I have 3 in the middle. And of course, if such a trisecant is not until it gets canceled with an adjacent trisecant, it will preserve a type. So here we have it. So if we do it geometrical, we will have 3 types of Z2 generators, and we will have a map. Well, not quite a homomorphism, but from GN3 to Z2 times Z2 times Z2. It's a very easy map, but now I hope I convinced you. I hope I convinced you that we have easy maps to free products of groups. Now, I want to say that this map, once again, how is this map constructed? I take all triples of indices 1, 2, and 3. Excuse me, all triples of strands corresponding to components 1, 2, and 3. And for such triples, I take those 3 strands, and as for other strands, it doesn't matter. And then I take all generators 1, 2, 3, 1, 2, 4, 1, 3, 4. Well, generators which have at least 2 indices among 1 and 2 and 3. So I take such generators, and from them I can get a lot of information. I can get some free products of Z2s. And then for such free products, I take their conjugacy classes. The word problem is obviously solvable. And also permutation of indices. So for example, if I have, well, I already drew it and wrote it, A, B, C, D, I can change generators, okay? And the statement is that this map is invariant under Markov moves. And if it is invariant under Markov moves, then it gives an invariant of braids. And actually, this is quite easy to prove, because if we perform the first Markov move, then something is on the top and something appears on the bottom. And if I read the word from the top, and if I read the corresponding word from the bottom, those two words will be the same but in opposite order. Okay, so this means that my element in the corresponding group gets conjugated. But one very important issue is that what we have inside, so if we conjugate beta by means of alpha, this beta, something on the top may get other indices. So instead of 1 to 3, they may become 3 to 1, which means that what I have inside can change its indices. So this means that our object will be conjugated, and so there can be both inner and outer automorphisms. But again, the word problem is solvable and everything easy. This is one thing that happens, and the other thing which happens is the second Markov move. But you see, for pure braids, the second Markov move deals with two strands of the same color, and from the point of view of this invariant, one strand is almost vertical, right? It's almost vertical, and the only thing when it's vertical, when it's not vertical, is when it wraps around and changes position with another point, with another line of the same color. But here I have a braid closure, and here I have a line which is completely vertical. So here, and so now I claim that this almost vertical line and this completely vertical line will give me the same impact into my sum, which is easily which can be easily checked. So this means that lots of terms will just get cancelled, and what remains will be the set of my initial braid on n strands, not n plus 1. Okay, so thus we get an invariant. So people having criticism may ask, how, well, isn't it invariant trivial? No, of course it's non-trivial, because if inside a braid we put some Brownian braids, for example, which is recognized by GN3 or GN4, by GN3, on 3 or 4 strands, one can see how the invariant changes. Also, it's quite easy to calculate for Brownian braids, because if I have a Brownian braid on n strands, well, I recall that Brownian means that whenever I well, for example, Borromean rings. Whenever I delete any strand, well, okay, I will not draw. Whenever we delete any strand, the braid becomes trivial. And this means that if we have, for example, 3 strands for Borromean rings and 3 closing strands, then the only choice which is essential is to take 3 initial strands, because if I take 2 strands which are initial and 1 strand which is closing, which is vertical, then the braid will be trivial. So, for Brownian braids, it's very easy to calculate, and this is more or less the same as GN3 invariant of Brownian braids. Okay. So now you see that it's non-trivial. Bad news is that it is invariant under link homotopy. It means if we are allowed to cross the component with itself, because if we have 2 links which change by a cross, which differ by a crossing change, then they can be represented by braids which differ by a crossing change. And that's a problem. So that's a problem, well, meaning that our invariant is not good enough from the point of view of just isotopy, but it's already an invariant for link homotopy. Okay, this is the proof of the main result. Now, what can we expect to do for further research? So first of all, there is an intriguing question what to do with knots. Because for knots, it's quite hard to enumerate anything. It's quite hard to get a way of enumerating strands, but I'm now thinking about that, and maybe if we have some progress, we will tell about it. It is expected that this invariant may be good in detecting knot invertibility. Why? Roughly speaking, if we invert the orientation of the knot, everything will get inverted. So somehow we will, all my words will get to words in the opposite direction. So they have to be palindromes, and they have to cancel with words in the opposite direction. So somehow it will be quite visible that something is not invertible if we do something for knots. Also, it seems that it should work for cobordisms. Actually, there are many questions concerning this construction. So maybe we can choose not only 3 strands, but maybe we can choose n strands if we have a link in n components, or maybe we can choose more, and maybe are there any other ways of fixing the problem of 2 different lines, 1, 2 on the same plane. So you see, there are lots of questions, and one more conceptual question is, how is it related to the Kontsevich integral? Why am I talking about the Kontsevich integral? Well, you see, when I consider knots in R3, such a knot, if it's a Morse knot with horizontal levels and horizontal tangent lines, then I have braids in each position, and I create chord diagrams, and then I paste these chord diagrams here. But here I would have something like triple chord diagrams. Unlike the Kontsevich integral, I have a group here. I don't have a graded ring, but maybe GN3 invariant can be somehow represented by an integral, and maybe there will be a chance to get an iterated integral here. Also, there are questions: are there any triple analogs of Vassiliev invariants? Are there any analogs? So actually, yesterday I was talking to Barnatan, and the first question he asked me, how is it related to Vassiliev invariants? I don't know so far. What is the triple analog of the chord diagram algebra? What is the triple analog of the Vassiliev relation? What is the triple element of the Knizhnik-Zamolodchikov connection? So there are lots of questions here which I still don't know how to answer. And I think that's all what I wanted to say. Thank you very much for your attention.
Yeah, thank you. I have one question. In the previous page, you take a braid beta and we add trivial n strands more, and we consider strands
Yes.
between xi0, x2n plus 1 minus i0, and xi1, x2n plus 1 minus i1.
Yes.
Then it is the closure, I mean, not the closure in Artin braid sense, but it is looks like flat. I forgot that we add the top and bottom, right?
Yes, well, it looks like a plaid closure, and there is a question. Maybe there is a way to construct a knot or braid invariants by using plaid closures, yeah, and the moves for them. It's the analog of Markov theorem. Maybe you can succeed in it, but here the reason for adding those strands is to handle the second Markov move. I will get lots of new summons when I have one vertical strand. And I have to one strand which is almost vertical. And those summons will have to get canceled with something. And they will cancel with something when I take this closure. So that's why I take two n strands, not n. Yes, and you see, so many things of that. If I don't want to have so many indices, many things of that can be visible if I just make distinction between 1, 2, 3 with 2 in the middle, 1, 2, 3 with 1 in the middle, and 1, 2, 3 with 3 in the middle. So I can already take them to be generators. And this will be Z2 times Z2 times Z2, and this group is already good enough. Yes, and one more comment. It seems like the same can be done for the G and 4 approach when I look not at only at horizontal trisecants, but also at horizontal circles passing through 3 points. And one more comment, yet another comment, is that somehow GN3 theory, maybe GN plus 1 3 theory, contains the usual braid theory. If I take one strand, if I pull one strand to the infinity, then if I have points here, then this infinite point, when I take it together with I and J, and take a screen here, then the usual crossing on the screen in the Artin sense will correspond to the crossing coming from infinity. So this will be my generator I, J, infinity. So just a small part of generators will correspond to Artin crossing. So somehow my GN3 generators contain many projections of braids from each point of view. And actually, from this point of view, we, together with Igor Nikonov, constructed a way of upgrading the Burao representation by using some virtual knot techniques. And possibly, it is known that Burao gives rise to the Alexander polynomial. There is a question whether we can upgrade the Alexander polynomial by using techniques given in today's lecture. So you see, we have, instead of just having one screen and drawing usual crossings, we have many screens from the point of view of from any perspective. And this information is much richer than the information we get just from usual diagrams with usual crossings.
Okay, thank you.
Thank you for. Are there any further questions or comments?
Okay, thanks. Okay, thank you for a nice talk, and see and hear you in a plural form in next weeks, and so next times of our seminar. See you again on our seminar.
Thank you very much. Thank you.